Hi everyone. In this video, I'm going to be talking about the particle in a box or infinite square well, which is a situation, a hypothetical situation, which is very useful for considering some of the concepts and mathematical tools of quantum mechanics. So what exactly is this situation? So let's set up a position graph. So this is position x, and let's say that we have a particle that is confined to a certain region from 0 to the length L. So we'll say this is a box with length L. So what this means is we're going to say that there's a particle in here and it can't get out of this box. There are walls here that it cannot penetrate. So it can be found somewhere in here. And in quantum mechanics, we're not sure exactly where it will be. It doesn't have a definite position. And so yeah, let's try and mathematically define what it means to be confined within these walls. So we can say there's a potential energy in this region, and we'll say that it takes on a value of 0 between 0 and L, and it takes a value of infinity everywhere else. Now, how exactly does this confine the particle to this region? Basically, if it wants to go outside of this region, it would require infinite energy to do so, and that's not possible. And so that's why this potential energy setup allows us to say that the particle is confined to this region. And now we're trying to figure out what our possible wave functions are. Now, the wave function is related to the probability of finding a particle in a certain place. So to be specific, the square of the wave function gives you the probability distribution for where you'll find the particle. So we already said that the probability of finding the particle outside of this region is 0. So everywhere else it's going to be 0, and we don't know what's going to be happening here. It's going to be doing something, and we don't know exactly what. So this is something that we're going to be figuring out over the course of this video. So psi of x is going to be 0 outside of this region, and we're going to figure out what it is between 0 and L. Now, to do this, we're particularly interested in finding the energy eigenstates in this setup. I will be going into more detail about what that actually means right now. So in order to start talking about energies, we have to introduce the Hamiltonian. Hamiltonian is an operator in quantum mechanics, which is meant to represent the total energy in a system. So Hamiltonian is in some sense going to be equal to the kinetic energy plus the potential energy. So classically, the kinetic energy is 1/2 mv squared, and potential energy we can say is v of x, which we already said is 0 inside the box and infinity everywhere else. And we're going to just be looking inside the box for now. We'll ignore where it's infinity, and so then this v of x drops away because it's 0. So 1/2 mv squared. I'm just going to rewrite this. So we know that momentum is equal to mass times velocity, and we can rewrite 1/2 mv squared as p squared over 2m. Let's just check this very quickly. mv squared over 2m is m squared v squared over 2m, and that's going to be equal to, you're going to cancel this, 1/2 mv squared. So p squared over 2m is what we're going to be using. And I mentioned before that the Hamiltonian is an operator. It's not just a value. So it's not just going to be equal to this energy value. Instead, we're going to use the operator called p operator, which is the momentum operator in quantum mechanics. And so I am not quite prepared to tell you what an operator really is and why we can use this in this way, but I will tell you for now, and you'll just have to trust me, that p operator is equal to I h bar d dx. So I is in fact the imaginary unit, the square root of -1. H bar is a constant. It's the reduced Planck's constant, which is relevant to things on very small scales in the quantum world. And then this is an operator, so you're going to apply this to something like a wave function, psi of x, and then you will be taking the derivative of that wave function with respect to position. So p squared over 2m is the relevant energy, and so we're going to write the Hamiltonian as p operator squared over 2m. I'm just going to erase the rest of this here. Okay, so p operator squared, let's first compute that. I just told you p operator is I h bar d dx squared. And that's going to be I squared h bar squared d squared dx squared. Squaring a derivative like this is probably not very mathematically rigorous, but it does work in this case, essentially. So this I squared is going to be -1, h bar squared d squared dx squared is what we get from that. So that's what we will plug in for the Hamiltonian. And we get h equals minus h bar squared over 2m d squared dx squared. Yeah. So now let's get back to how this relates to the particle in a box. So this is a version of Schrödinger's equation, which is an essential part of quantum mechanics. And I mentioned earlier eigenstates, the energy eigenstates of the wave function. So this Hamiltonian is an operator, and we defined it here. And this E sub n is the energy of an energy eigenstate. And so what exactly am I saying here? I'm saying that if we apply this operator, if we take the second derivative with respect to position of some psi n, and then multiply it by minus h bar squared over 2m, then we will get back that same psi n, that same wave function, multiplied by some quantity, which is the energy associated with that state. Now, this may not be very clear, but I will be going ahead to show you what that looks like, what we might take for psi of n, what energy values we can find there, and how exactly they satisfy this equation. And I'll just add to the confusion a bit more here by telling you that there are many such states. There are many states that allow this, and so we're going to write a general formula for them, which looks like this. The square root of 2 over L, remember L is the length of the box, how large space we're allowing this particle to move, times the sine of n pi x over L. So now what I'm telling you is this is a solution to this, and I will be explaining this in great detail, but essentially if we use this Hamiltonian operator and apply it to this wave function, we will get back the same wave function and some other factor, and that factor is the energy eigenvalue associated with this eigenstate, energy eigenstate. So first, I'll just briefly talk about why we might think there's a sine x in the solution to this. The energy eigenstates would be have the form of something times sine of something else. And the reason for that is we're trying to take the second derivative. The Hamiltonian applied to this is going to be the second derivative of this psi n, and it should still return something that looks like psi n, because this is just a number. This energy is just going to be a number, not an operator. So somehow we're going to take the second derivative and get just a multiple of the original state. And sines allow this, because the derivative of sine is cosine, and then the derivative of cosine is minus sine. So you have just a multiple of the original thing back. And that's why it might make sense to expect our psi of n to take the form of something times the sine of something else. And this isn't the only thing that satisfies this, where the second derivative is a multiple of itself. There's also cosines, there's also e to the power of something, and these are all very closely related through Euler's formula, which is a pretty incredible thing and very useful in quantum mechanics. I've used it many times in my class for quantum mechanics. So that's just an interesting side note. We won't be diving into that right now. So yeah, let me try and explain next why there's this factor of the square root of 2 over L. And first, let me maybe erase this. Before I even get to that, let me first mention, why is there an n here? Why are there n's all over here? I mentioned earlier that there are many such eigenstates, and essentially we want to be able to plug in different values of n and find different eigenstates. And essentially applying this operator to any of them would give us some energy times the eigenstate itself. And those values of n can vary a lot, and we're going to actually find that n can be 1, 2, 3, or any positive whole number. And I will come back to why that is a little bit later. So I'm trying to decide what I can erase. I'll just trace everything for now and rewrite what's relevant. So let's rewrite this bit. Okay, psi n. Okay, so now let's justify why we have this root 2 over L here. I mentioned before that in quantum mechanics, the square of the wave function gives you the probability distribution. And so this is telling us if we square this value, if we square this function, we'll get the function for the probability distribution. And a probability distribution always has an area under it of 1, because if it's telling us that the probability of any outcome is 1. Not that any given outcome, but that the probability of some outcome out of the set of possible outcomes, basically something that is possible has to happen. I'm not sure if that's a very clear explanation, but hopefully it's a pretty intuitive concept anyway. Sometimes wave functions will be complex. There will be values of I in here, in which case, instead of squaring it, you would do psi n times the complex conjugate of psi n. In this case, since psi n is real, that's equal to psi n squared. And so we chose this, or I wrote this down and learned it from other people, because this satisfies the fact that psi n squared equals 2 over L times sine squared of n pi x over L. This has an area under it. This probability distribution has an area under it equal to 1. And so let me just quickly demonstrate that, maybe not that quickly. So recall that this is the value that it's taking on when 0 is less than or equal to x is less than or equal to L, and outside of this region, psi n equals 0. Yes, so the area under this curve is going to be the integral from minus infinity to infinity of psi n squared dx. But since it's 0 everywhere except this region, that's going to be equal to the integral from 0 to L of psi n squared dx. I'll just erase some of this and continue. So we have the integral from 0 to L of psi n squared dx. That's equal to 2 over L times sine squared n pi x over L dx. This is an integral from 0 to L. We can take out the 2 over L, integral from 0 to L, sine squared n pi x over L dx. This is something else that I probably should have mentioned earlier, but this solution was also chosen in order to make sure that psi of x is continuous. So psi of x to be continuous, we know that it's 0 everywhere else. It has to be 0 if x equals 0 or L, because it's 0 outside of those regions. And so if it was non-zero at those exact points, then there would be a discontinuity, and we don't want a discontinuity in psi of x. So we can check that for any value of n, we have if x equals 0, then this whole thing equals 0, and then sine of 0 is 0. So that works. And then if x equals L, then we have n pi, and the sine of any multiple of pi is also 0. And so that's one reason, another reason why this is the function that was chosen. So given that fact, we also know that this is that sine squared of n pi x over L, that this between 0 and L, this is experiencing an integer number of wavelengths, I suppose. I apologize that the wording is not coming to me. Essentially, the options that we are looking at here are from 0 to L. If n equals 1, then we have sine of pi x over L. And in the region from 0 to L, this ranges from 0 to pi, and 0 to pi looks like that for sine. If n equals 2, then it's 2 pi x, and it'll go something like this. 3 pi would be something like this. I apologize that these are all overlapping, but the idea is that we're getting an integer number of integer number of kind of humps and downward humps of the sine wave between 0 and L. And so sine squared, all of these humps are going to go above 0. So let me just draw this again for sine squared. So sine squared, it's going to look something like this. That's the n equals 3 case, but they're all going to be above. And so instead of evaluating this directly, what we can do is find the average value of sine squared over any of these humps. And so one way that we can think about this is that the average value, so we know that sine squared of x, well, maybe let's not use x, let's even use, because this is a general case, plus cosine squared theta equals 1. And so the average value of sine squared, we also know that the same situation with humps would occur if we used cosine squared. I hope that's clear without me going through it explicitly. But basically, the average value of sine squared, let's just call that average value of sine squared, equals the average value of cosine squared. And if we add these two together, that would give us 1. And so what do we need to add together? So 2 times something, let's call the average value of sine squared theta a. The average value, 2 times that equals 1, and a equals 1/2. So that is the average value of sine squared theta over any integer number of humps. So the average value of sine squared theta is 1/2. So this integral is just going to be equal to the length given by this integral times 1/2. And so that's, the length is from 0 to L, so that's just L times 1/2. And these 2's cancel, these L's cancel, and we just get 1. And recall, this is the integral from 0 to L which is also equal to the integral from minus infinity to infinity of psi sub n squared dx. And recall that the goal is to normalize this so that the probability distribution would have an area of 1 underneath it. So this has worked well. And you can see that it required this value of 2 over L to cancel the terms inside. And that's why we chose the root 2 over L at the beginning here. So that was a rather long tangent. Next, I wanted to look at, what do I want to look at? Next, we want to find the values of E sub n associated with each of these eigenstates. So first, we want to just see what H applied to them is going to be equal to. Let's actually erase a little bit more here. So let's recall H equals minus H bar squared over 2m d squared dx squared. So H psi n equals minus H bar squared over 2m d squared dx squared of root 2 over L sine of n pi x over L. Apologies if that's a little smushed. So what's this going to give us? Let's first take out the root 2 over L. We can have minus H bar squared root 2 over 2m root L. And now the derivative of this, well, each time we differentiate, we're going to take out, first of all, sine differentiated twice is going to be cosine and then minus sine. So we're going to have minus something times sine, but so we're also going to be pulling out this factor, n pi over L, twice. N pi over L twice, and then it's going to give us back sine of n pi x over L. One more parentheses, lots of parentheses. And this is going to be, let's see, what can we cancel here? Not all that much. I had forgotten that we mostly just want to keep everything, yeah. So we're going to have minus H bar squared, n squared. Actually, let's get rid of this minus sign. We can cancel, this is a plus, this is a plus. H bar squared, n squared, pi squared over 2m times L squared here. You notice I didn't use these, and so we're going to have root 2 over L sine of n pi x over L again. And notice that this here is just back to being psi n of x. And so this right here, recall, the goal was to have the Hamiltonian applied to psi n gives back the energy eigenvalue times psi n. And see, we've gotten something times psi n and this was by applying the Hamiltonian to this. So this piece right here must be the energy eigenvalue. And that's h bar squared n squared pi squared over 2ml squared. And yeah, I feel like I probably didn't do the best job teaching this. I will probably come back to it and make it again, hopefully a little smoother and a little clearer. But yeah, that tells you the energy eigenstates. So essentially, if you write, if you find that there's a wave function such as this for a particle in a box, these well, the possible energies you could measure for a particle in a box are these values right here, and n has to be an integer. And this is like one of the really defining features of quantum mechanics, is that you can't just measure any energy. It has to be like n has to be an integer. This is not continuous. You can't pick any value of the energy. If n equals 1, you will get h bar squared pi squared over 2ml squared. If n equals 2, you'll get 4 times that. And there's no nothing in between. There's no possibility to measure an energy in between those two. So that is essentially all I have to say for today. Thank you.